Welcome back to day 2 of this year's Labs, Leaders, and Critical Connections. And a warm welcome to Professor Cynthia Wolberger at Johns Hopkins School of Medicine. She is in many ways a modern-day Rosalind Franklin. Please read her impressive bio on our website, but suffice it to say she was well-trained in biophysics at Cornell, her PhD at Harvard, and postdocs at UCSF and Johns Hopkins. Her brief video is the perfect tutorial about Rosalind Franklin's now famous photograph 51. In many ways, the cornerstone of her own work and her research using X-ray crystallography to develop three-dimensional models of proteins. Let's start with that.
Here's a brief explanation of what we learned from Rosalind Franklin's famous photograph 51. Rosalind Franklin was recording fiber diffraction from DNA. She placed long fibers of calf thymus DNA in an X-ray beam and recorded the pattern of scattered X-rays on film. There's a mathematical relationship between the particular characteristics and parameters of the DNA helix and the pattern of spots one observes on the film. So it's possible to just take an image like this and learn quite a bit about the nature of the helix that scattered those X-rays. The first thing we learn from this photograph is that DNA is in fact helical. This characteristic X pattern is what one observes when one places a helix in the path of the X-rays. The second thing we learn from the photograph comes from the position of this dark spot over here. From the distance from the center to the dark spot, that tells us that the fundamental repeats of the helix are 3.4 angstroms apart, or in the DNA helix, it's a 3.4 angstrom rise per base pair. The spacing between these sets of spots over here, known as layer lines, gives us the pitch of the helix, and the pitch is 34 angstroms. So the pitch is the distance going vertically here that the helix repeats itself. And now if you take the pitch of 34 angstroms and divide by the rise per base pair of 3.4, that tells us that there are 10 base pairs per turn in the helix. Now, if we look closely at the layer lines, you actually see that there are missing spots on this fourth layer line. With a single strand of DNA, you would expect to see spots here as well. The missing layer line tells us that there's more than one strand wound around one another, and that those strands are not symmetrically placed. So they're asymmetric, and that was the clue that there's a major and a minor groove in the DNA. Finally, the spacing between the spots gives the helix radius, and so you calculate a radius of 10 angstroms or 20 angstroms, which is really exactly the diameter of bDNA. And you can read about all this elegant work in Franklin and Gosling's classic paper, which was published in the same issue of Nature as Watson and Crick's. So Rosalind Franklin and her work were really an inspiration to me when I began graduate school in the early 80s. And that was the time when the model of bDNA was actually experimentally verified. So in Rosalind Franklin's time, it wasn't possible to actually determine the X-ray crystal structure of bDNA. And that was for two reasons. One is there actually weren't the methods yet to determine structures of anything bigger than, something like penicillin or something like that. But the other was that there really weren't methods for synthesizing uniform fragments of DNA, which is what you need to grow a crystal. And that technology was developed in the latter part of the 70s. And it was in the early, I forget, 1980 or 1981 that Dick Dickerson and his colleagues determined the first structure of bDNA, a full three-dimensional structure, so independently determined without any assumptions and model building the way one needs to do with fiber diffraction in Rosalind Franklin's time. And so that was a really exciting time for me as a new graduate student starting to learn X-ray crystallography. And it also made it possible to go to the next step, and that was actually to determine structures of proteins that bound to specific sequences of DNA and regulated transcription. And that was something that I worked on in graduate school. The protein was called 434 CRO from phage 434. That was the topic of my thesis. And it really it was a new era in structural biology then, the ability to make these pieces of DNA, look at these complexes, and really understand not just the structure of DNA or the structure of a protein, but how together it gave rise to these genetic switches. And so when I began my own laboratory here at Johns Hopkins, I continued work on bigger pieces of DNA, bigger complexes, trying to understand combinatorial regulation of transcription. And that brought me through over the years to examining other related topics like chromatin modifying enzymes. We also became interested in ubiquitination and its role in regulating transcription, and to where our laboratory is today. So the newest thing that burst on the scene in the last decade was cryo-electron microscopy, and or cryo-EM as it's known. And cryo-EM uses some of the same really fundamental underlying mathematics and diffraction theory to determine structures, as does X-ray crystallography. So it was a natural transition for people like me who are trained as X-ray crystallographers and for years just used X-ray diffraction. And cryo-EM is now enabling us and many other people in the field to go to the next level, to look at larger and larger complexes and determine their structures, and through that structural information, understand how a variety of biological processes work. The interest in my lab now is of understanding how chromatin modifications are attached. So looking at structures of these large enzyme complexes bound to nucleosomes, understanding how they attach modifications like methylation and acetylation and ubiquitination, and understanding the crosstalk between ubiquitination of histone proteins and then how that then triggers enzyme complexes to, say, methylate DNA. So a recent structure that we'd worked on a couple of years ago was the structure of DOT1L, which is one of these chromatin modifying enzymes that recognizes the ubiquitin, and the ubiquitin in some way stimulates that enzyme to methylate a particular residue in DNA. Other enzymes we looking at are also stimulated by ubiquitins such as compass, MLL1. And so these are building upon this earlier foundation of looking at structures of DNA, how the DNA is recognized, how larger complexes with DNA, so a nucleosome, which has about 147 base pairs of DNA wrapped twice around this protein disk, and how those modifications are deposited, and in turn, those large enzyme complexes, how they recognize the nucleosome, how they're positioned in a precise way, and how you can get crosstalk between one modification and another.
Thank you so much, Cynthia, for this wonderful time travel and connecting photograph 51 to real breakthrough research now with cryo-EM. We're so grateful for your research and for your participation today. Now, please stay tuned for the next session of our conference.